in a very general sense. Okay. Say if this is a surface, or say this is a surface. To begin with, this is a surface, and these are two sides of the surface. The pressure here on this side of the surface is P1, and the pressure on this side of the surface is P2. Right? Now, for this surface to assume this shape, what is required? Say this was a surface. The pressure on one side, on this side was P1. Whatever there was, let's say there could have been a liquid on one side, gas on the other side, irrespective. Say for some reason there is pressure P1 on this side and there is pressure P2 on this side. If P1 is equal to P2, then this surface will remain like this only, right? But what would be the condition for this surface to bend this way? P1 has to be more than P2, isn't it? Because if P1 is more than P2, it will create a bulge like this, isn't it? For this bulge to be created, very clearly, P1 has to be more than P2. Yes or no? For this bulge to be created, very clearly, P1 has to be more than P2. Yes or no? So if there is a curved surface, this part is called the concave side of the curved surface. This is called the concave side of the curved surface. And this side is called the convex side of the curved surface. Alright? So the pressure on the concave side will be more than the pressure on the convex side. The pressure on the concave side will be more than the pressure on the convex side. Right? Now, this being the basic idea, what I'm going to look at is a liquid drop, and surrounded by a medium that has pressure P0. There is a pressure of the liquid Pi, which is the pressure inside the liquid drop, and I want to obtain an expression of the difference in pressures. A spherical liquid drop having a property T, surface tension T. I want to figure out the difference in pressures between the concave side and the convex side. The concave side for a spherical drop would be points inside the spherical drop. The convex side would be points outside the spherical drop, right? I want to find the pressure differential. I want to be able to find the pressure differential. The inside pressure would be in excess of the outside pressure, because the outside belongs to the convex, the inside will belong to the concave. I have now a liquid drop, and I want to find the excess pressure inside the drop. I want to be able to find the excess pressure inside the drop. This is what I want to, right? So, inside a drop of liquid of drop means spherical. Drop of liquid of radius r and having surface tension T. Radius r, surface tension T. This is a liquid drop. Just a drop. It's not like it's placed in a metallic sphere and so it's just a liquid drop, right? Just a liquid drop. The drop has been created owing to surface tension, right? And it has a liquid inside it. This entire region would be the concave side. The region outside would be the convex side, right? Where would you expect the pressure to be more? Inside the concave side. In the concave side, the pressure would be more. In the convex side, the pressure would be less. Right? This is what we determined. I want to find the excess pressure inside compared to the pressure outside. The pressure outside, let's say, is atmospheric. The pressure outside is atmospheric, so P naught. P naught, say, this is atmospheric pressure. Or it could be something else also. Does not matter. Say it's atmospheric. My intention is to find the pressure difference between the inside and the outside of a liquid drop having surface tension T. So, say the pressure inside is Pi. The pressure inside is Pi. I want to find Pi minus P naught, excess pressure inside is Pi minus P naught. Pi minus P naught is the excess pressure inside. I call it delta P. Now, a pressure Pi inside and a pressure P naught outside is like zero pressure outside and a pressure Pi minus P naught inside. In terms of the force exerted on this surface, right? Because this is exerting a force radially inwards, Pi is exerting a force radially outwards. Yes or no? P naught, atmospheric pressure, is exerting on any element here, on any area element, right? P naught is exerting on any area element, a P naught into, let's say this area element is dA on the surface, this way, and this is exerting on this a force on this element which is going to be Pi into dA. Yes or no? So what's the net force on this element? Pi minus P naught into dA outwards. Pi minus P naught into dA outwards on this. So it's as if there is no atmospheric pressure and the pressure inside is Pi minus P naught. Can I do that? So this is equivalent to saying, that in this liquid, as if there is no atmospheric pressure, but the pressure inside is Pi minus P naught. Pi minus P naught is the pressure inside. Equivalent. And there is no pressure outside. That's the equivalence. There is no problem with that. Now, I want to compute Pi minus P naught. My intention is to compute Pi minus P naught given T and the radius R. Given T and the radius R of this spherical droplet. Radius R of this spherical droplet. What I do is, so this is like Pi minus P naught inside. What I do is, I look at a free body diagram of this sphere. I have to expose surface tension now. I have to expose surface tension. So with a view to exposing surface tension will not be a bulk property. It will be a property only for the surface of this sphere. Right? What I do is, I create a free body diagram of a hemisphere. Half of the sphere, which is this, I'll create a free body diagram of any one half. I'll create a free body diagram of either of this half or this half. Either the dome to the left of the equator or dome to the right of the equator. I'll create a free body diagram of any one. Right? So what I do is, let me create a free body diagram of this portion. Let me create a free body diagram of this portion. So if I create a free body diagram, let me call this portion 1, let me call this portion 2. If I create a free body diagram of this portion 1, if I create a free body diagram of this portion 1, now, what are the external forces? It'll experience force because of the pressure of this side. It'll experience a force like this, right? There is pressure to the right, which is Pi minus P naught acting on this surface. Pi minus P naught acting on the circular surface. I'm talking of external. So when I draw free body diagram, I look at external forces. I don't look at the forces because of the pressure here. Those are internal forces. Will not feature in my free body diagram, right? What has happened? Whatever is happening inside in the interior of this hemisphere is not external. Will not appear in the free body diagram of this hemisphere, right? This hemisphere will only report what it experiences from this hemisphere, right? This hemisphere will exert on this, through this surface, a force Pi minus P naught into pi r squared. Pi r squared is the area of this exposed circular region, yes or no? Force is pressure into area. The pressure is to the right is Pi minus P naught, and that pressure is acting on this circular area, right? This is my circular area, this is my circular area, and the pressure here is Pi minus P naught acting on this. How much force will be exerted on this? Pressure into area, right? It's acting on this, yes or no? Pi minus P naught into pi r squared, right? Now, but the goddamn thing is in equilibrium. I mean, it might make you believe that, hey, this will accelerate to the left under the influence of this force. Doesn't, because what happens is, look at this liquid surface. Look at this liquid surface, right? There is going to be perpendicular to this surface tension. This is a surface. So there is going to be on this surface tension acting this way. Yes or no? Do you realize? There is going to be, so if I had to just straighten it up, no? If I had to straighten this circular portion up, then it will be like, so it's like there is T acting this way on this circular portion. Right? Yes or no? There is T acting over how much of circumference? 2 pi r, right? The circle, right? Yes or no? T acting over this 2 pi r, isn't it? This is 2 pi r. So the force because of surface tension acting on the circumference is going to be T into 2 pi r. T into 2 pi r, yes or no? Which will just be balanced by this, right? So this is delta P, pressure differential between the inside and the outside of this spherical drop. So delta P into pi r squared is T into 2 pi r. So the pressure inside is in excess of the pressure outside by an amount 2T by r. R is the radius of the curvature, radius of the curve of the surface. T is the surface tension. That means if the pressure here is P naught, what would be the pressure here? P naught plus 2T by r. The pressure inside would be in excess of the pressure outside by an amount 2T by r. The pressure on the, in general, the pressure on the concave side will be higher than the pressure on the convex side by an amount 2T by R, by an amount 2T by R, right? Yes or no? Right? Do you understand what has happened here? Huh? Everything, na? Huh? I mean, the hemisphere to the right will exert on the hemisphere to the left surface tension forces this way only, na? Pulling forces on this circumference only, na? This is how it's going to exert, right? On the circumference T into 2 pi R, right? There is, so this was a liquid drop. This was a liquid drop. One could look at the same thing from an energy perspective. Pressure, excess pressure inside compared to the pressure outside from purely an energy perspective. Let me put it, because it's important to understand this energy perspective also. How I could have obtained the same result from energy considerations, surface energy considerations. Take a look at this. Huh? So, look, this was my liquid drop. This was my liquid drop, right? I'm not drawing the liquid inside, it clutters the whole thing. And this was of radius R. This was of radius R. Contains liquid. T is the surface tension. Pi is the pressure inside. P naught is the pressure outside. Now imagine, mentally imagine the radius to, just mentally imagine the radius to increase by a small amount dr. Mentally imagine the radius to increase by a very small amount dr. That means r plus dr is the new radius. This then becomes my bubble if I mentally conceive this, right? And of course, I've already told you Pi has to be greater than P naught. Now, Pi minus P naught acts radially outward. Pi minus P naught acts radially outward along the normal to the sphere, right? Right? And what is the work done by this? First of all, what's the radially outward force? Can I not say the radially outward force is Pi minus P naught into 4 pi r squared? Is that not the radially outward force? Right? Right? And if this force acts outwards, causing a displacement dr of this boundary, what's the work done by this force? Into dr. That's the work done by this force. This is the work done by this force. Now, this is not a dissipative work. Work done by a force must manifest itself in some form or the other. Either work done by a force will manifest itself as change of kinetic energy or change of potential energy. I'm imagining that there is no change of kinetic energy. So this work done by the forces because of the pressure on the sphere, it must appear somewhere, na? If I raise this, I have done some work to raise it to this height. Will this work go waste? No. It will appear as potential energy of this mass, isn't it? Right? If I have not added kinetic energy, I have raised it very slowly. Then I have not brought in kinetic energy into the picture. I have only added to the potential energy, right? So if this force is doing work by radially expanding the boundary of the spherical drop, right? Then this must appear somewhere. Where could it appear? Where could it appear? It must appear as change in surface energy. That's the only place it must appear as change in, because the surface area has changed. The surface area has changed, isn't it? So this must manifest itself as change in surface energy. Change in surface energy is what? Surface tension into change in area. Yes or no? What would this mean then? How does one compute change in area? Hey, area is 4 pi r square. Hmm? So dA is going to be 8 pi r dr. Can I say this? dA is going to be 8 pi r dr. Algebra of differentials. So if you say dA dr, that's going to be 8 pi r, isn't it? dA dr is going to be 8 pi r. So dA is going to be 8 pi r dr. No? So this is t into 8 pi r dr. So now using this and this is my delta P. Excess pressure in the concave region compared to the convex region. Delta P, as you can see, is 2T by R. This is from energy considerations. Excess pressure inside is 2T by